our two main examples where we started looking at conformal field theories and having a grasp of how they look like were toy models, or very simplified examples just to see how things work a little bit. And one of them was a toy model for the kind of things that you should expect when you deal with a conformal field theory in perturbation theory, where you have some free limit and then you start doing Feynman diagrams and doing loops and so on. And typically at tree level you are doing with just connecting stuff by propagators and so on. So you just draw something like what you have here, where each of these points represents a bilinear, a composite operator that schematically is like phi squared. It's an operator of dimension 2. You just unite them by a bunch of propagators. This is the propagator in 4 dimensions. You get some simple rational function of the positions that then you go, and after taking out some well-defined space-time dependence, you expand into some well-known functions known as conformal blocks that describe the transition from a group of points to another group of points of all the operators that can flow in the CFT. And if you manage to decompose your trivial propagators in this form, by looking at what multiplies the conformal blocks, you can read off the interactions between the two external scalar operators and the separator non-trivial operator that is flowing in the middle, which in this case can be an operator with spin. So this was one example, and as you remember, we compared then the spin operator computed by brute force versus extracted from the conformal bootstrap, and everything was good. Then we did another example where we took our toy model to be a toy model describing massive particles in anti-de Sitter space, anti-de Sitter being a space-time where you can think that the boundary is the world we live in, and then there is some radial direction z. And we threw geodesics out. Okay, we put some epsilon to regulate them, but that's not very important. And then we throw off geodesics. They will meet at a given point. And the rules of the game was for each segment, it's weighted by e to the minus the mass times the length of the particle. That's the propagation of a massive particle in any space-time in the semi-classical limits. And then we minimized, we found the position p such that this action was minimal, such that the contribution would be maximal. And that gave, remarkably, some constant that depends on the interaction strength, that measures the interaction strength, that in this case depends on the 3 deltas, that's fine. But more interestingly, we got that even though this was not put by hand, suddenly what appears, which geometrically in this picture is not obvious at all, are the differences between x1, x2, x1, x3, and x2, x3 to exactly the powers that should come out if you were in a CFT where under this toy model correspondence, the dimensions and the masses, the dimensions in the bulk and the masses in the boundary are to be identified. So this is, if you want, our ADS CFT toy model, where we use ADS to define, if you want, the CFT. Okay? Now, of course, I mean, here we were not very worried about the overall factor. I could postulate that I say my particles interact, and when I meet, there is a coupling G. And then our computation would be perfect, except I should multiply my computation by G. Okay, that's fine. That's just a normalization. Now, even this result was not unique because we decided that our toy model describes rules where particles move in ADS and then they meet at a point, and if they meet, there is some probability amplitude G, and this is our interaction. But the interaction could be different. It could be that the 3 particles meet, and when they are interacting, the interaction depends on the angles on how they are meeting. Right? Interactions in space, when particles interact, it's not always scalar contact interactions. Sometimes you have derivatives. Right? You have vertex operators that contain derivatives that want to know from which directions particles came. So I could have decided that everything is the same, the minimization problem will be the same, but then I could further complicate things a little bit and say the interaction is not just a number, but it can say depend on the angles, how the particles are joining and so on. Nothing would change here, but then this G would be a slightly more complicated dependence on the deltas and so on that would take that into account. This would even be more obvious if now we were to continue our games and try to come up with what could be the rules if I were to describe, say, a 4-point correlation function, which is more interesting. And now it's up to me. I could define the rules to be such that particles go, then there is a vertex with some coupling G, and then they annihilate again and they go to the boundary. This could be one set of rules. If I postulate, if I define that my interactions in ADS are such that there are only cubic vertices, right? And I could put them to depend on the polarizations or not, and then I would minimize over the position of the interaction points. But I could also have, if I want, why not, I could also decide to have contact interactions where the four particles meet with some coupling that I could arbitrary coupling. It's up to me. Again, I'm defining. I'm creating a toy model and then defining. And all these kind of possibilities, all this plethora of interactions in EDS, there are many, but that's fine because there are also many CFTs in the boundary. So it's better. So we have some freedom for coming up with our definitions for what happens inside our crystal ball and getting different theories, different effective theories on the boundary, generating therefore different, a priori different conformal field theories. Okay? And as I said, let me just comment once again because this is an important point. Typically the modern point of view on EDS CFT, when it is used in this perspective that we know one side and don't know the other. No, actually it's not true. I was going to say typically, but I should retract myself and say sometimes what we want to do sometimes is not use the bulk to define the boundary, but rather use the boundary to define the bulk, because typically we control much better the space of conformal field theories than the theories of quantum gravity. So solving a theory of quantum gravity is much more complicated than defining a conformal field theory on the boundary of a space-time. Okay? However, for example, people that do say this thing that you might have heard, ADS condensed matter, which is coming up with some phenomenological models starting in ADS and then defining some effective rules for the boundary, what they are effectively doing is coming up with some phenomenological rules and defining whatever comes out as some magnetization and some response theory and so on, and they are more doing this kind of toy model point of view where they have some effective rules in the bulk, they put some Einstein gravity and some fields and so on, and whatever comes out is the definition of the outcome of the CFT. So there are both points of view. Very good. Then something that we are going to discuss at length today is the statement that once you write a conformal bootstrap like we did here, you can do it in different channels, and this provides important self-consistency conditions. So let me first write down something that I wanted to add, because there was a question, and I was not positive about what the answer to that question was, but it turns out that the answer is very simple, so let me mention. And the question was, here we impose some constraint. We said that a CFT, so we define the CFT as a CFT data, a set of data, such that the algebra of the OP is associative. And this fancy thing just means that you can take the OP of 2 points such that the algebra is consistent. You can take the OP first of these 2 points or first of these 2 points and the result doesn't matter. Okay? So in cartoons, this means that if I take a 4-point function, I can expand it as a sum over all my operators, and this is equal to a sum over all my operators in this channel. And then there was a question by your colleague that is not here today about whether 5 points would give new constraints. Do we gain anything by going to 5 and higher points? So it's trivial that we don't. Let's see. So what we want to do, let's just see that we don't get anything new for 5 points. Suppose we have 1, 2, 3, 4, 5. Okay? Now let's OP in points 1 and 2. Let's take 1 and 2 close. So let's do it. So we sum over the operator O. We encircle 1 and 2. So we sum over O. And the other ones are on the other side. So 1, 2, 3, 4, 5. Do you agree? So here what we did is we had our 5 points and we just did the OP of 1 and 2 and left the other ones. But now we can again, now we have here a 4-point function, we can again apply the OP and write this as a sum over operator O and O prime. 1, 2, 3, and here we have O, here we have O prime, 4, 5. Do you agree? All we did was use the OP now for this 4-point function. Again, write this 4-point function as a sum over whatever flows between 4 and 5 and the rest. But now, look here. This is a 4-point function here. And now here, use this relation. So this becomes equal to the sum over O and O prime. And now inside this box, we use this move that allows us to put 1, 2, 3, O prime, 4, 5. So here we use the 4 point that we established already. Do you agree? And now this is nothing, but now if you collapse again this O, this is, or no, sorry, if you collapse again the bottom, this is nothing but 2, 3, and then a blob in the bottom where we have 1, 4, 5. Do you agree? So what we establish is exactly what we want. We can take the OP of point 1 and 2, or the OP of point 2 and 3 and get the same thing. And this is not a new constraint. It is a consequence of 4 points, you see? It's not new. Remember, you were asking whether 5 points was a new condition or not. And I'm just coming back to what you were asking to show that it doesn't matter. You can take the OP of 1, 2, or you can take the OP of 2, 3, and the result is independent. And this establishes that indeed checking the consistency of the OP for 5 points is not a new constraint. Okay? So it's just very simple. There was no point in leaving this open. Okay, now I'm very optimistic, and I think that today I will probably be done in 40 minutes or maybe 1 hour. So I thought, but you tell me whether this is pointless. I thought it could be good because it seems like not everyone was totally comfortable with this, reviewing why it is true that propagation of a particle is just given by e to the minus mass times the length. Why is it true that once we have a propagation of a particle, x, then we have the propagation of a particle, our usual propagator, y, this is the usual propagator, why is this equal to a sum over paths e to the minus mass times the length of the path? This is the essence, if you want the first quantization. Is this something that is worth reviewing? This will take me like 15 minutes to review, or we can just end the lecture a bit earlier, and you all saw this more or less, and you don't need to. What do you prefer? It's really up to you. I mean, it's just that I had the impression that not everyone knew. Who would like me to go through this derivation of why this is true? 1, 2, 3, 4. Who would rather that we move on and then we come back to this at the end if needed? 1, 2, but you don't count. You saw at the very end of the lecture. 1, 2, 3, 4, 5, 6. Okay, so most people would rather that I would just jump over this. So if you want, I have it written down just at the very end. Come look at this paper and it's more or less obvious. Very good, great. So then let's move on to analyzing this conformal bootstrap that now we see very well that for 4 points it is totally sufficient. So let's try to understand how much mileage could we take out of it. Okay? And our goal in today's lecture would be to learn something about the three-dimensionalizing model, which is a conformal field theory for which we have very few tools. It's a theory that is the endpoint of an untrivial RG flow. It's not something that we can use naive perturbation theory around the free theory. It's a strongly coupled theory. And the approaches that people do to study the three-dimensionalizing model is, for example, by starting in 4 minus epsilon dimension, where the Ising model is weakly coupled, and then trying to follow epsilon, which is a small parameter, all the way to 1, such that you go to 3 dimensions. Or starting with Ising model in 2 dimensions and doing 2 plus epsilon and trying to follow it from 3 dimensions. It's not the best, because, okay, it's a small parameter, but then you will put epsilon to 1. It's not ideal. Or people do say Monte Carlo and try to do numerics and try to understand if they can reach the critical point of the Ising model by numerics. So it's really a point that is challenging. It's not something that we can start, write down the lattice model, and do step after step after step, and in a straightforward way arrive at the exponents. And here I'm going to show you some novel perspective on trying to attack this model that has been extremely fruitful in the recent years, and that nowadays competes with Monte Carlo, which is a method that has been pushed by Slava Ryzhkov, David Poland, and collaborators, which is based precisely on these bootstrap ideas. So let's do it. Okay. So the conformal bootstrap is the basic idea that, it's written there, that if we take a correlation function of 4 identical operators, imagine we have O at x1, O at x2, O at x3, and O at x4, we can expand it in 2 different channels. And this is the equation that we have to solve. And I want to emphasize it's not a cartoon, it's really an equation. This is just this stuff here, it is just this equation here. I put delta here instead of 2 such that I could use this equation here. So this is just that equation. And this is that equation with 2 and 4 exchanged, which in practice means going there and changing 2 and 4 in the prefactor and then changing z bar by 1 minus z, 1 minus z bar, because the cross ratios u and v are precisely related by changing 2 and 4. So we really have that equation equal to that equation where the prefactor has 2 and 4 exchanged and the sum of blocks has z and z bar replaced by 1 minus z, 1 minus z bar. So it is an equation. And from that equation, it follows, after separating the contribution of the identity, so I separate out the contribution of the identity. I write that as 1 from the identity. The conformal block is 1 and so on. Remember, we wrote when we have the identity what happens in the yesterday. So we write 1 plus the rest. We equate both sides. And this is the equation we end up. That is going to be the useful equation to work with. So let me write and then it will become clear. We isolate the identity and we put it on the left-hand side. So this, the 1 comes from the contribution of the identity. And here is the equation that you get. You get 1 is equal to a sum over all primaries of dimension delta and del, but not the identity. The identity we took out. The structure constant square between operator O, which are the identical scalar operators, and your operators that could a priori have spin. Let's say O with some delta and some L. And then here we get V to the dimension of your external operator. Oh, this is the dimension of the external operator, times the conformal block for delta and del of U and V, minus U to the dimension of your operator times the conformal block delta and del of V and U. Here I could use z bar, then I would write 1 minus z bar, divided by U to the dimension of our operator minus V to the dimension of your operator. Okay? So let me just explain a little bit where this equation comes from, in case it's not totally obvious. So note that when I equate both equations, it does become an equation for cross ratios, because you see that I write this equation equal to the same thing with 2 and 4 exchanged. And then the ratio of these prefactors is nothing but U over V to the power delta. Right? So this U over V, this U's to the deltas and V to the deltas that are there just come from precisely these prefactors. Okay, so I divide the equation, say, by this term here. Then on the other side, I have U over V to the power of delta. So that's where these factors of U to the delta and V to the delta come from. And the identity comes precisely multiplied by 1 minus U over V to the delta. And then when I divide by, that's why I get this denominator. So, okay? So I just don't want to do boring algebra, but can everyone see by head where this comes from? I mean, you should really be able to literally see it just by looking at the equation and doing it on your head. Is it okay? Do I have any wrong sign? No, right? I put when things change sign, they change sign. That's why there is V minus U and U minus V. So everything is good. So these are the so-called conformal bootstrap equations. And this combination here, remember that these conformal blocks are just some hypergeometric functions. These are also some hypergeometric functions, just change U and V. So in the same way that the conformal block is known, all this stuff is known. So, okay, well, let's call this, I don't know, straight F. And this straight F is a function of U and V. What else? It's a function of delta and del of the exchanged operator. And it's also a function of the dimension of the external operator. Let's put in the exponent, delta O. Okay? So it's a known function. If you give me these three numbers, delta of O, delta of the exchanged guy, and spin of the exchanged guy, I can write this function as a bunch of hypergeometrics. Is it okay? So this is totally known. It's like our cosine, sine, Bessel function. It's the same thing. And this is unknown. Okay? So these are the so-called bootstrap equations. And these define infinitely many equations for infinitely many variables which implies that this is hard. Right? It's a hard problem. It's a functional equation. You have infinitely many equations for infinitely many variables. What are the variables? They are the CFT data, the dimensions and the structure constants, and you have to solve these equations. So you can think of this equation. Suppose to make it into a tractable system, I decide to say that this equation must be true for u and v belonging to some table of numbers. I just say let u and v be 1/2, 1/2, 1/3, 1/3, 1/3, 1/2, and I make a huge list of 1 million points. Then at each of those points, this equation must be true. And of course, you can make an infinite list. So you just have an equation that you can evaluate this equation at any point u and v, and this equation must be true, so you have infinitely many equations. And you have infinitely many variables, which are the CFT data, which are the structure constants, and the spectrum. And the basic idea is that you can think of these equations as defining a cone. Let me explain. The key point is that because of this square here, these numbers are positive. And because these are positive, the way I can think is that I have a linear combination with positive coefficients times some infinite dimensional vector space, which is the vector space of whose base is these conformal blocks. Right? So this defines a vector space. And what I have is a linear combination with positive coefficient of vectors in some vector space. This is the definition of a cone. Imagine you have a linear combination of this vector and this vector, right? And this one. Then this defines a cone like this. Any positive coefficient, so it must go up or inside the cone. It cannot get out the cone if you are summing vectors with a positive coefficient. So when you are summing vectors in a positive coefficient, let me write a toy model that makes it more obvious what I want to say. The problem that we are studying is something like this. We have a sum of pi, where this p stands for positive. This is our 3-point positive. And this depends on some parameter delta. So this delta will be some parameter. Actually, these guys, which should be positive, times some vector, which are these complicated functions in this formal vector space, some vector I, and this vector depends on some parameter delta. Right? Our known functions do depend on delta. So then what we have is we want to ask if this is equal to 1, which in this formal sense is a vector in this vector space. And we want to ask, can 1 be written as a sum of vectors which are these conformal blocks? Okay? So what do we have? We have this stuff that defines a cone. If this were my vectors, right? If I have some vectors like this, a sum of positive coefficients times my vectors defines some cone. Let's do it with 2. Right? If I sum positive coefficients times vectors, I define a cone. In general, this defines the inside of this space. It defines a cone. And then the question is 1 here or is 1 inside the cone? Okay? So this cone here is a delta-dependent cone. My vectors are moving as I'm changing delta. But 1 is fixed. This 1 is fixed, so I should rather have drawn 2 cones instead of 2 1s on the same cone. Okay? Is it okay? Do you allow me to do this slide shenanigan? So we have our vector 1. So let's draw 2 pictures. I feel bad. Sorry. And the other option is we have 1 here, and we change the cone, and now the cone is here, and 1 is not inside the cone. So if your vectors are such that by defining a cone, 1 is not inside, then you are good. You don't even have to try. You know for sure that you cannot satisfy these equations. You know for sure that there is no solution to this equation here. If your vectors define a cone that 1 is not inside, you will never find p's that solve it. So here, this delta is impossible. Okay? And this means that we rule out the existence of CFTs with this delta. So if we can find cones where the identity is not inside the cone, we rule out the CFT. What about here? Here, we cannot say that there is a CFT, but we can say maybe there exists a CFT with this delta. So the basic idea of this method is not to find precise conformal field theories, but to carve out the space of CFTs, to establish bounds, to say, these regions of deltas, forget it. You will never find a physical theory with these dimensions, with these critical exponents. But this one, maybe it's going to be okay. So what we are going to do is to say, for example, we say, suppose we plot here the lightest operator. And here we plot the next to the lightest operator. If you want to have an example in mind in the Ising model, the lightest one will be the magnetization, the spin operator, and the next to the lightest will be the energy density in the Ising model. Okay, these are the two relevant operators corresponding to magnetic field and temperature deformations. Is it okay? And then what we will be able to do is find some curve where here we have maybe, but here we have no CFT for sure. And we will be able to establish bounds that will tell us where can we have physical theories and where can we not have physical theories. And here we cannot have CFTs for sure, because if delta of our lightest operator versus the delta of the next to the lightest is here, it is such that these equations over there can be thought of as defining a cone that doesn't contain the identity. Okay? Now, if you know a little bit about computer science, you know that this problem is a typical problem in what's called linear programming. Okay? So basically what you want to do is find linear operators that act on your space of functions, and you want to find linear operators that act for a given choice of deltas when acting here give negative numbers. So if you find something that when acting here gives negative numbers, and when acting on the identity gives a positive number, you reach a contradiction. So if you find that for some deltas there exists a linear operator that acts on one to give something positive and acts here to give something negative, you are good. Then you reach the contradiction, because then you have positive equal a sum of positive coefficients of negative numbers, and that's impossible. So that's now a problem that you can put in a computer. You can write the most general kind of linear functional. You write a very linear functional. What's a linear functional? It's, for example, take your object and evaluate your object at 0 plus evaluate it at 1. This is linear. Or take the derivative of your object. That's also linear. And you can make a big base of such functionals, right? And then for a given space of functionals, the bigger the space, the better will be your numerics. For a given space of functionals, you look for functionals which on acting on this give something negative, such that, and when acting on one gives something positive. For example, imagine my functional is the average of whatever I act on 1/3 and 1/4. That definitely gives 1 when acting on 1. But it could be that for this hypergeometrics it gives something negative. Who knows? We will have to plot it to see. And then we would have a contradiction, because if it's true that the average of two conformal blocks of this thing is negative for a given range of spectrum, but this is clearly positive, that spectrum is ruled out. Do you agree? This is, the first time you hear, I understand that this is kind of a reasoning, at least for me, it took me some time to absorb, because it's very different from the kind of arguments we are used to. At the end, it is simple, but it's just in a different axis from what we are used to thinking as physicists. So please tell me if it's a little bit confusing still. Sorry? Because we want it to go through the structure constant. A better way of saying would be to say that do you agree that if it's a linear functional it works? Because if you find a functional such that f of 1 is bigger than 0, and it's a linear functional, and then you find it such that some of delta and f. F is functional of this sum. My notation was like this. Right? You have this. And now what do you want to be able to do? The next step. You want to be able to bring the functional down here. That's why you need linearity. So because now you want this to be equal to the sum of delta and L, the structure constant squared, times the functional acting on these hypergeometrics, f and L. And if you can find a functional, a linear functional, right? If you find a linear function with a property that this thing is negative for some spectrum, this is spectrum dependent statement because depending on the spectrum, these objects are different. So for each spectrum, you try to find some functional that makes this negative. If you find it for a given spectrum, if for a given spectrum you manage to find such functional, you know this CFT cannot exist. Because this would lead to a contradiction. Right? So if such functional exists, if we find this implies that the CFT does not exist. Right? So if the functional exists, the CFT does not. Right? Like the city is only big for one of us. Right? Either the functional or the CFT. You cannot have both. So if you could fail to find the functional, then maybe you didn't search hard enough. But if you find whatever functional it is, it's ruled out. No one can save it anymore. Because someone else might not be able to find the functional, but who cares? Right? So if you don't find, it doesn't mean much. It just means that maybe you didn't work hard enough. That's why these bounds just give maybe here. Who knows? Maybe you were not very smart. But whenever you find a functional, it's okay for sure. There's no error bars, there's no improving, there's nothing. If you found the functional, you found the functional. For sure you excluded that. So maybe you can do better, but you cannot do wrong. Okay?
Why is the plot just plotting the lightest and next to lightest? Wouldn't this be a plot of the whole spectrum?
Yeah, it would. This is just the simplest example.
Yeah.
Okay. Any question? I really would like you to make sure that you ask me if it's not clear, because yeah. We are going now to continue on with this kind of logic for a little bit. So let me write. What we are interested in, but please continue thinking about the question, is about the Ising model. So in the Ising model, the two lightest operators, the two most relevant operators are sigma, which is the spin or the magnetization. By the way, the Ising model is in the same universality class of the transition of water from liquid to gas. In that case, sigma would be the density of molecules. So we have this spin and this magnetization, and in the OP of sigma with sigma, we have the identity, we have the energy density. This guy is an odds operator, right? The spin points up or down, and under parity it flips. And odd times odd must give even, and indeed 1 is even, epsilon is odd, plus other stuff that are heavier. When you make epsilon with epsilon, you get energy density. So this is the lightest operator that appears in the OP of sigma with sigma. In the Ising model, it's the energy density. Is it okay?
Yeah, I'm not familiar how the expansion looks like for Ising model.
Okay. So sigma is, we don't know, that's precisely what we want to do. We want to avoid knowing anything about the Ising model. We want to solve it, but we don't want to write down a lattice model. That's hopeless. Sigma is the lightest scalar operator. It is odd. This is the magnetization. It's an experimental fact. Yes. Epsilon is the lightest operator in the OP of sigma with sigma. Because these guys are odd, epsilon is even. In the sigma with sigma, there is an operator. The lightest one, let it be epsilon. No? I cannot do better than this.
First how to define what is epsilon, and second, why is this the lightest?
Definition. Epsilon is the lightest operator appearing in the OP of sigma with sigma.
So we don't know yet that this is energy density.
Then I'm telling you that, okay, this is the lightest operator. It's an even operator. Anything that can appear unless you have a good argument should appear. So whenever you take OP of two operators, you produce everything compatible with your symmetries. You are not expected to not to produce something, right? I mean, that would mean that the 3-point function of your sigma sigma with an operator is equal to 0. If it is 0, you have to explain why. Why a priori can't I get a 3-point function between sigma and an operator? So epsilon is the lightest operator which appears in sigma and sigma, but it's also very reasonable to say it is the lightest even operator. Otherwise, there must be some hidden symmetry that explains why the 3-point function of sigma sigma with the lightest even operator is 0. So assuming no degeneracies, epsilon is the lightest even operator. Now an experimental fact. How do you go to the lab and go to the Ising model at the critical Ising model? You go to your lab, you take your magnet, and you have to tune magnetic field. If you turn on magnetic field, the spins will all be up or will all be down depending on the direction of your magnetic field, and you don't go to a critical point. So you tune the magnetic field. The magnetic field is odd. What does it mean that you have to tune it in the lab? It means that in the blackboard, there is a relevant operator. So this relevant operator in our CFT, in our quantum field theory, is sigma. It is an operator that has a direction, the magnetic field. Okay? But there is something else you have to do in the lab. You have to go to the Curie temperature. So there is another relevant operator that corresponds to the energy density. That is the only other relevant operator, because we only need to tune these two things experimentally. And this operator should be the lightest operator, and therefore we identify it with epsilon. I could repeat the same words for water and vapor. There I would have to tune again two parameters to have the transition between water and vapor. What is it? It's the pressure and temperature, which would be the analog of this sigma and epsilon again. Okay? Do I answer your question? But morally speaking, if you want to think of it in terms of the field theory, if you want to think of it, let me start at 4 minus epsilon dimension, where the Ising model is almost free. And then I have some field theory, which is basically 5 to the 4 theory, where I have a double well and I study the critical point close to this double well. Then sigma would be related to phi. It is my order parameter that tells me the magnetization. And the epsilon will be related to phi squared. But that's not real. This is really the physical way I think to think about it. And sigma with epsilon, it doesn't contain the identity. It's sigma plus dot dot. Well, this is at least some very basic things, just based on watching water boil. Now, what do we know about the 2D Ising model? The 2D Ising model is solved exactly. What do we both do about the 3D Ising model? Much less, as I said. So let me write for both.
Is it possible to write, for example, epsilon operator epsilon in terms of sigmas? For example, in terms of just usual.
Roughly speaking, it's sigma squared, roughly speaking. But you see, the operatorial definition of an operator is not physical. In the lab, you are not measuring how does epsilon look like in terms of sigma. Right? And that makes sense because this is a strongly coupled field theory. You wrote a Lagrangian, and now you can try to write epsilon in terms of sigma. Then you have to do so much renormalization, so much strong coupling, so much things that, okay, this original definition that you started with, this bare definition, you have to do so much renormalization, so much massaging, that until you get to a physical quantity, it's so far away from what you started with, it's a bit useless. Unless your theory is weakly coupled, who cares about the form, how the operators look like? You just care about physical questions. What is the correlation function of 4 spin operators, 4 magnetization? I measure my magnetization in my magnet in 4 points. What should I get in average? This is a physical question, right? So I really don't think you should try to think. But if you want, epsilon is sigma squared, morally speaking. Okay? It is just like if you write, for example, imagine you have a free field and you write, what's the OP between phi with phi? what would it contain? Well, I can contract phi with phi, so there is the identity. And then I can just write phi square at the point 0 plus derivatives and so on. So this definitely appears in the OP of this with it. So this would be kind of the analog of this, but this is kind of the strongly coupled version of this. So I should not try to take it too seriously. So 3D, 2D Ising model. So we have the dimension of sigma is equal to 1 over 8, dimension of epsilon equal to 1, and here dimension of sigma equal to 0.5183. There are error bars here. And dimension of epsilon is 1.412. There are error bars, of course.
This is theoretical.
This is theoretical, and the other one is experimental, if you want. Yeah, from Monte Carlo, from so-called epsilon expansions, from really taking a piece of material, so on, whatever you want. Let's take this as being experimental, and this as being theoretical. Okay, great. And what I'm now going to do, or to show you what we can do, is try to see how could we try to find these points, try to find something close to these points, just knowing that my theory contains sigma, contains epsilon, and contains no other relevant operators. As I said, this is an experimental observation. In the lab, you only have to tune magnetization and temperature. Okay? So let's write, what do we know about the spectrum of my theory? Let me write the spectrum, and let this be the spin. What do we know about this plot here that you saw in the first week? Can someone tell me something?
There's the unitarity bound.
There is the unitarity bound. So we need to have dimensions bigger than a certain value. So there is a line here, which is the line L plus D minus 2. And for a given spin, let me see what I have here. 0, 1, 2, 3, 4. For a given spin, my spectrum is somewhere here, but not below. For a given spin, my spectrum, this is where I should try to look for theories, but never below, if I want a unitary theory. Okay? And for 0, I should, for spin 0, it's a slight exception, that this value is 1 so it's, sorry, what do I have here? It's D minus 2 for 4 dimensions, right? So what do I have here? So the unitary value is D over 2 minus 1, right? Which is how much? When I have 3, I have 1/2. Well, why don't I have here 1/2? So am I missing some factor of 2? Can you check in your notes? Unitarity bound is D over 2 minus 1, right? I cannot see here. Sorry? Can you check? Can you look, please? Unitarity bound for scalars. You did it with Jami. I just forgot if there is an over 2. I mean, it's... No, so for D equal to... Sorry? It looks good to me, but let me check. No, D minus 2 over 2. Ah, so it's correct, yeah. So D minus 2 over 2. So it should be 1/2 for D equal 3. And for D equal 2, it should be 0. But actually, wait. Now I remember why I said this. Because No, that's it. Okay, that's correct, yeah. So it should be 0, okay. So let's suppose we do the 3D Ising model, there is this 1/2, and then I should be here. Okay, so we want to do the 3D Ising model, which is 1/2. If it was equal to, it would just be bigger than 0. So this is where our theories a priori could live. So we are not going to look outside this region, of course, we are going to look inside here. Okay? And now, let me just see, yeah. I'm going to consider the following linear functional here. I'm going to consider the following. I'm going to consider this equation, okay? And I'm going to consider the equation at z equal 1/2 z bar equal 1/2 plus 1/10, okay? Some strange value, but that's my choice, minus the equation evaluated at z equal 1/2, z bar equal 1/3. Okay, so I will take this, and I will also consider, I will do two linear combinations. I will consider this case, and I will also consider, and you might ask, why am I considering these strange values? I'll tell you in a minute, but mostly it's kind of random. It doesn't matter. You could do more or less anything you would like. And here, 1/2 plus 1/10 again, that probably can be simplified, minus the equation at 1/3, 1/4. Okay, so I'm going to consider this linear combination of two terms. Okay, so this means that because I chose to take the equation minus the equation with coefficient 1, the 1 drops out. Okay, and I get that 0 is equal to a sum of some positive numbers, this c square, OL, times a two-dimensional vector, v2, that depends on delta L and delta of my operator, which is just obtained by taking that object at this value minus that object at this value, and so on. Do you agree? Is it clear? This vector is just this function evaluated at those points minus this function evaluated at the other points, the first component of this vector. And the second component of this vector is just this function at 1/2 minus this function at 1/3, 1/4. Right? Is it clear? This is just definition. I could have, this is a simple functional. I'll just choose a two-dimensional vector space to play my games. I could have chosen something much more complicated, but I will show you that this already gives something fun that we can play with and see these cones, because this allows me to draw in the blackboard, because the blackboard is two-dimensional. But of course, for a computer, it's not very relevant, that. Okay? Is it clear? Yeah, it's important that this is clear. Yes? So we have a sum, 0, equal to a sum of positive numbers times a set of two-dimensional vectors. Right? So if all these two-dimensional vectors are pointing to the right, I can never get 0. Do you agree? If all of them are pointing to the right, they cannot add up to 0. Okay? So now, I will soon turn on the computer to show you in Mathematica so that you see that I'm not lying, but I'm going to just draw the plot of what we get. So here I will draw 0. So here is the origin. Here is a line that it will become clear why it is relevant. Okay? And right. And this is what the values of these vectors are. So the vector starts here and points here, and then starts here and points here. I'm drawing here the vectors smaller and smaller, the normalization of the vectors is not relevant. What matters is their direction. If I divide by a positive number, it doesn't matter for this argument. So I'm rescaling them on purpose, and I'm drawing them here, smaller and smaller, and there is one which is actually bigger here, and so on, and they form, and they condense in this direction, and so on, where this is L equals 0 at the unitarity bound, L equal 2 at the unitarity bound. We can only have even spin, so there's in the OP have two scalars, the identical scalars, so there's no point in doing the odd ones. L equal 4 at the unitarity bound, and so on. Okay? So this is what they are at the unitarity bound. If I put my fields at the unitarity bound, is this at the unitarity bound? Sorry, let me just check. Actually, one second. What have I done? So epsilon from 1 over 100 up to 4. Epsilon is L plus epsilon. L. Important. I'm doing this exercise now in 2 dimensions. Why? Because in 2 dimensions I know the form of the conformal blocks analytically, and I said that at 3 I don't know. At 3 I could do numerically, but that's already okay. That's something I could not do in one evening. So that requires solving the differential equation or something that you can always do, of course. But it's much simpler to do numerically for d equal to, and then conceptually nothing changes. You just change the form of the conformal blocks. And also it's very good to start with d equal to, because with d equal to we have numerical results. And this is how they look like at the unitarity bound. This is what they look like for the dimension of my sigma operator equal to 1 over 8. So I decided to put myself at exactly 1 over 8. Okay? And then plot this when at the unitarity bound, this is delta that is being exchanged. Right? So I have my vector that depends on delta and on delta of the exchange on delta and on delta of the operator O. Delta of O, which is sigma, is just 1 over 8. And the other delta I will play with, and first I start at the unitarity bound, and they are pointing like this. Okay? Just a little bit confused by something that doesn't make much sense. Give me 1 second. No, it makes sense. It's okay. Right. And then we start increasing the dimension. We start asking ourselves. So, and now, sorry. Yeah, this I'm being. Now we start saying, let's now go over these lines. We go over here and see how these points move. Okay? And let's do that. And as we go over these lines, what happens is the following. These spin operators, they move and they asymptote to some asymptotic direction. And they move, and they move, and they move, and they do something like this. Okay? And then the scalar operator, you can check, I wrote these vectors explicitly such that you can go home and verify because it looks kind of wild. Here is what the scalar operator, again, you just take this function, put spin equals 0 for 2 dimensions. If you want, I can write down the conformal blocks. It's roughly what we wrote last time. But you remember that for our conformal blocks, there was this z bar over z minus z bar. And I told you that in 2 dimensions, just take out that factor. It's roughly that. And for the scalar, something funny happens. As you increase the dimension, the scalar does this. And does this. Okay? This is what the scalar decides to do. The same point doesn't matter because here I'm not paying attention to the normalization. All I'm plotting, what is significant is just the direction. Don't pay any attention for them coming inside or outside. I'm not worried about the direct, the norm. Here in this graph, I'm plotting this 2-dimensional vector. So we are plotting these 2-dimensional vectors that depend on the spin, that depend on delta, and where this delta of the operator is 1 over 8. So we have a discrete set of vectors, and for each vector we take delta to go from the unitarity bound up. And this is what we find. And this value here, the value where they cross this point at delta equal 0.160883, and they cross this point at delta equal 1.03582. Okay? Is it clear? And now, you see what I want, look what we can immediately tell. We can say that there exists no CFT. Can you write with, can you see with this color? Yeah? There exists no CFT with dimension of my lightest operator equal 1 over 8 and dimension of my next to the lightest even operator bigger than 1.03582. This is impossible. It means that epsilon, in other words, it means that the dimension of epsilon must be smaller than 1.03582 for this value of the dimension of sigma. And why? Because if you say that the lightest operator is after this point, then all scalar operators are after this point. If the lightest is, then all are. So then it means that all your vectors are inside this cone. If that was the case, then all your vectors are on this side of the dashed line. They can never add up to 0 with positive coefficients. You need someone to be on the other side. So you need a scalar here for sure on this part. If you have no scalar here, there is no way these vectors, by just adding up these vectors that are all on this side plus this scalar in this side, there is no way you can add up to 0. Right? And this was choosing this trivial functional. Now I could try to play with a functional and see if I get better bounds. But this is a bound for sure. This is a physical property of nature. In nature, I will never find a CFT where delta of epsilon is bigger than this value. This I will never find for sure with this delta of sigma.
What do you mean it's a property of nature? It's a property of the CFT.
It's a property of conformal field theories, yeah. I will never find a conformal field theory where my lightest operator has dimension 1/8 and my next to the lightest has dimension 1.1. This cannot happen. This critical exponent will not exist. Do you agree? What about this one? Does it mean that the lightest operator must have dimension bigger than this point? Or not? So just to see. What's the relevance? So this is about the second time that it crosses, right? So if everyone is after this, we are in trouble, because then there's no one on the other side, we cannot add up to 0. What about the significance of the first point? Can someone tell me? Sorry? So can you ask what happens after this point? So I'm telling you, this line here, if you see, if all vectors are to the right of any line, I just draw this one because it's a useful one, because it's the one where if it's smaller, it will touch this point here. So if it's more tilted like this, so it's the best line. So you cannot have all vectors to this side. Otherwise, you cannot have them. So this is the point where it crosses, the first time it crosses this dashed line. So I want to ask, can we say something about the spectrum from that second point? From the first point, from this 0.16? So this is one answer. Can someone tell me, is this answer correct? This is a bit, I understand this is a bit different. This was what, I actually am emphasizing this point because once I said this in a lecture and then the next lecture I had to say that I was confused, because that's wrong. So you must be careful. Don't think that. It doesn't mean that the operator must be heavier than that. You could have 10 operators here before reaching that point, provided later you add one operator here that will make sure that you could solve crossing. So no one forbids you to have operators before this point. It's not that the lightest one needs to be after this point. You need to have one on that side of the line. But you could have some already before. So no, this point does not have significance. It's this one that has significance. From this point of view of bounds, it's the second one that matters. The second one tells you if everyone is after the second, we are in trouble. But we could a priori have one operator with this dimension, one operator with this dimension, provided we have one operator with this dimension. This is the guy that comes to save the day, to make sure we can solve the equations. But there was no problem in having these two vectors here. They can be cancelled by some vectors here plus this one.
I said the heaviest one must be after this, not the lightest one.
The heaviest operator must be after that point. The heaviest operator must be after that point. That's true. Yeah, okay, that's true. So sorry, okay. So, but okay, so then let me say what I thought you said. What is not true, what we cannot say, is that the lightest operator is after this point. This you did not say, and that's good. One should not say. I said at some point once. Okay, but not today. So we need to have a scalar here. That's all we can say. And this is something very cute. You see that we just decided to plot these vectors. See, instead of turning on the computer, I'll just show you. So you see, I drew here these vectors going there, 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 there. I go around the unitarity bound, and here is the scalar operator. It goes here, crosses this, and comes back to some point here. So these 2 points here is where I must for sure have a scalar after this dashed line. Now this was for this delta sigma. So now what we can do is go to various delta sigmas, change delta sigma, and for each delta sigma repeat this exercise. Right? So I did this manually. So I did 1, 2, 3, 4, 5, 6 points. And this is what you get. Here you can have a CFT. Here you cannot. It's excluded. Okay? So what we find, just based on this simple example, I really want to leave this and this on because this is if you want, and this one as well. So what we found was that, just based on this example, we get some plot like this. Okay, it's kind of cute there, and here is the correct point. Okay, and this is the bound that we are getting. You see, for example, this point here, what we got was 1.0 what? 1.04, right? This 1.03538, whatever. And the correct value is indeed very close, is at 1. And here was 1/8. Okay? This was a bound. And then, now if you would use a better space of functionals, so this was our bound. Our bound is here, 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 here. We did a couple of sigmas, and then I just unite them. Okay, and this is our bound. So here, up here, there is no CFT. Right? And now you could imagine, instead of doing a two-dimensional bound, a two-dimensional vector, I'll choose now, I will scan all possible two-dimensional vectors. Right? Now I put in a computer and I say, instead of computing at this 1/2 plus 1/10, let me compute at 1/5. And I see, for 1/5, do I get a better bound for any of these points here? And now I let the computer start changing these values and trying to find the best possible bounds. And then instead of using 2 dimensions, I use 3 dimensions, which is better. And I impose if it is now to the right of some plane and not to the right of some line. And now I have 3-dimensional vectors, right? There is a plane, and you cannot have all the vectors to the right of a plane. One must be to the other side if I want them to add up to 0. So then in a computer, as you see, I can put now a multi-dimensional vector space with multi-dimensional parameters, have the computer scan, and look for the optimal values within my general class of ansatz. Is it clear? So this is what linear programming does for you. And people did it, and they found a bound, and the best bound is better than ours. But again, I want to emphasize that the bound must be below ours. Our bound is rigorous, it's perfect. It's really, I mean, even though it looks very hand-waving with some crazy numbers like that, it's a true property of CFTs. The one they got is better. It goes down and so on, and then it actually does something very cool like this. And the Ising model sits right at the kink. So there is this cusp here, and the Ising model is spot on there. And when people saw this, they said, wow, this is kind of cute. We know that there is a theory there. So, and it's exactly at the kink. If we look at the coordinates of the kink, we get perfectly 1.00001/8, and perfect matching with that. And then they said, can it be that it works in 3 dimensions? Because now we just plug the conformal blocks in 3 dimensions. And indeed, when you do it in 3 dimensions, here is the plot that you get. This is from a talk from this year at Strings, where so that people see that at string theory we are doing serious nature things. So from Simon Duffins, and what do you see here? You see a precise cusp there, and somehow the printer didn't print the x's, I don't know why. But this point of the cusp is precisely at the experimentally measured dimensions of the operators of the 3D Ising model. So this was kind of expected when you saw this kink, that perhaps you would find the same thing. But then, recently, and this is the second slide of this string talk, people went further. And this was all coming from analyzing sigma, 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 sigma. But this is not the most general conformal correlation function that I could create and try to study the bootstrap. And then people ask, what if I now study sigma, sigma, epsilon, epsilon as well? And this is what are called mixed correlators. Okay? And now you can take these guys together and analyze, browse in your space of conformal field theories, sigma, 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 and sigma, sigma, epsilon, epsilon as well. Okay? And what you do is you browse in this space, assuming the operators are above the unitarity bound, and assuming that you have only 2 relevant operators, sigma and epsilon. And then you see, what's the space that I get? And here something quite spectacular happened, which was that instead of getting an upper bound like here, so this was a strictly upper bound, what is absolutely spectacular is that once you add mixed correlators, instead of upper bounds, you get islands. What do I mean by this is that if you plot the same kind of result in the same axis, what you find is that there is this point, 0.5, what was the experiment result? 183, 1.4, 1, 2. Here is the point that you want, and the bounds tell you that it is there, and you cannot even see. It's really absolutely amazing, and you have to zoom in, and once you zoom in, you see that there is some shape, and this is the shape of allowed conformal field theories. And here is the plot that they generate so that you see that this is not a joke. You see? The Ising model must be between 0.5181 and 0.5183. I don't know. For me, this is the paper of the year. It's really something absolutely outstanding. That you can really, just based on the conformal bootstrap and on having 2 relevant operators, pick out, you see this is the point, and the CFT must be inside this island here, this thin island, and you see that it must be really 0.518. There's no way out. And if there is a phase transition of water, this must be its critical exponent. And this is the other one, 0.1412. So with 3 digits, you can get, by exploring the space of functionals, in this kind of operators. So this is where we stand in conformal field theory in higher dimensions. This is an example that we can do in 3 minutes in Mathematica. As soon as you want to explore big space of functionals with mixed correlators furthermore and so on, of course it doesn't get as simple as this. Now you have to really implement this linear programming. There are numerical methods for doing this now, this codex or whatever, I forgot, simplex, I forgot the name. And okay, then it starts to be heavy. You again need to go to clusters and so on. But it's beautiful that the underlying principle is really so simple. Let us see, we could get to it in 4 lectures, and we got really to everything we basically needed to do this very advanced computation. And it is an unperturbative definition of CFTs that doesn't care about the underlying particular lattice implementation and so on, that goes directly to the infrared, that goes directly to the strongly coupled physics, that just asks, I want to solve it directly in the infrared. I am at the CFT, at the final endpoint of the RG flow. I don't care about starting with the lattice and fine-tuning everything. I go directly to the endpoint. I just impose consistency of my CFT. I impose that I only have to tune temperature and magnetic field in the lab, and I get spot on this island. And this was exploring sigma, 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 and sigma, sigma, epsilon, epsilon. Now maybe if you start exploring now the higher operators that you found already using this bootstrap, maybe you can start to shrink more and more and more and more until you really squeeze it. And right now this island intersects already Monte Carlo. Monte Carlo is already bigger than this island. So you could already exclude values of Monte Carlo just based on this island. I mean, I think that now a bit important question is how can we do this analytically? How can we understand something about the bootstrap analytically? The bootstrap was proposed by Polyakov when he, in 71 or a very long time ago, when he really said, these are beautiful equations, this should be useful and so on. And then it was dormant for like 20 years. Everyone thought he was dreaming, and then it was revived by Ryzhkov and friends that started using it for completely different purposes. They started studying the space of conformal field theories because they wanted to show that some completion of the standard model known as Technicolor could not hold. And they did it by showing that the dimension of the operator that people wanted to add to the action doesn't exist. And so it was a purely phenomenological motivation, and then it went on to this more kind of condensed matter applications. And it is a method that now competes with Monte Carlo. So now it's important from a conceptual point of view. It would be very important to understand better physically why do we get an island, at least to understand why should we expect to get an island. This was a surprise for the community when they come up with this paper and said this is an island. Well, and why? At least understanding why in one case it's an infinite domain and in one case it's an island, at least this we should be able to understand analytically. I mean, at least that. Why there is a kink? I mean, we should be able to understand why is there a kink. So there are many important questions, some of them quantitative, like let's try to get even better bounds, let's try to look for other kinks to study other phase transition, like in helium and the O2, ON models, let's do precision bootstrap, that's one direction, but the other direction is also let's understand better analytically. And yet another direction is how does this talk to the first part of the talk? How can we use the bootstrap to guide us doing our weak coupling analytic computations? Is there any connection? Is there any connection between understanding the spectrum and the dimensions analytically in weakly coupled field theories and the bootstrap? So far it has not been very useful. It is useful for these theories where we have no analytic handle, but what about the theories where we do have some handle? Can we also use it and help us check things or go even further? What about in ADS CFT? What about in N equals 4 Spreng-Mills? What about in studying quantities like Wilson loops and scattering amplitudes in conformal field theories? So this is just the beginning. We are now exploring finally for higher dimensional conformal field theories. It's something that I think it was an accident of history that people found 2 dimensions and they saw this infinite symmetry and then 4 dimensions at 15 generators. So compared to infinite, who cares about higher dimensional CFTs? 15 generators, what's this? If in 2 dimensions I have all this infinite algebra, holomorphic, anti-holomorphic functions and so on, and then string theory appeared and all this power of 2 dimensions to study 2-dimensional CFTs. At the same time, QCD appears as governing the strong forces and the world was not conformal. And then it was a bit forgotten. And then I think it was partially because of the recent developments of higher dimensional CFTs, most notably because of N equals 4 Spreng-Mills and the developments of CFTs because of ADS CFT, that this interest in higher dimensional CFTs got revived. And we are now redoing many of the things that could have been done 20, 30 years ago. And there is a lot of catching up to do, and there are a lot of interesting and exciting things, I think, awaiting to be discovered, and it's up to you now. Thank you. We are done.